All right, good morning, everyone. Morning, yeah, still morning. Y'all doing okay?
Doing good. How are you?
Doing good, doing good. Busy, busy. Okay, so any questions before we begin today's material? Everybody happy? Okay, well, in that case, if you change your mind, just let me know if you have a question. I don't know why this looks so small. Let me see. Maybe I'm zoomed in. Hold on a second. No, that's right. Okay. All right. So last class we were talking about antiderivatives. Talked about how we should know some from Cal 1. You know, our knowledge of Cal 1 helps us in Cal 2 finding antiderivatives. Like the antiderivative of secant squared x would be tangent x plus some constant, because we know the derivative of tangent is secant squared. And then we finished up talking about this thing called the power rule. So I just want to start there. I want to make sure everyone's clear with the power rule. For antiderivatives. And let me just check. Yeah, I started to talk about it right at the end of last class. So basically the power rule says that if little f is equal to x to any power n, then the antiderivative, the general antiderivative, capital F of x, okay, so this is our antiderivative, will be equal to, and we knew that the power had to go up by 1, which is the opposite of taking the derivative. Instead of subtracting, we have to add. And then we also have to multiply by 1 over n plus 1, because that will take, when the n plus 1 comes out, when the power comes out, when we take the derivative, the 1 over n plus 1 will kill that power off. And so we'll just get a 1 in front, and then plus a constant. Now, this is true almost always. There's one case where n, if we pick a certain n, then it won't work. Can somebody tell me what n this wouldn't work for? And maybe why?
Maybe -1.
Yeah, -1. So look, if we try and plug -1 in right here for n, we're going to get -1 plus 1, which is 0, and we can't divide by 0. So this formula always works when n is not equal to -1. Now, if n is -1, so let's look at that special case. If n is equal to -1, then what we really have is that little f of x equals x to the -1, which is really 1 over x. And do we know the antiderivative of that?
Would that be ln of x?
Yeah, that's natural log. So that's, again, from Cal 1, we know that when we take the derivative of natural log of x, we get 1 over x. So we are going to put here natural log of, now I'm going to put the absolute value around the x, and this is what we're going to do from here on out. Anytime we take the antiderivative of 1 over x, we're going to put natural log of the absolute value of x, because the natural log has some domain restrictions. And in our little function, little f of x could be a negative number, right? But if we plug that in here, we're going to get natural log of a negative number, which won't work. So we put absolute value that way, it doesn't mess up the domain, and then plus c. So we have the power rule, which takes care of all powers of x except -1. And then in the case where we have -1, well, we already know the answer. Okay, so we are covered. Every power of x now can be, we can find the antiderivative of it, all right? And that's what we did at the end of class last time. We took this example, we worked through it. So let's do another example. And I really like to put problems like this on exams. Something like if little f of x is equal to 2x plus the square root of x minus 4 plus x cubed all over the cube root of x. Okay, so let's get something clear before we start. We know from Cal 1, okay, just a quick little summary here. We know in Cal 1 that if we have two functions added or subtracted together and we take the derivative, that we can just do the derivatives separately, right? If I have two functions added together, I want to take the derivative, then I just take derivative of each one, right? But if we have a product, we do not just take the derivative of each one, right? We have to do the product rule. I mean, life would have been good if this were the case, right? In Cal 1, if there were no product rule, but that's not the way it is. We actually have to apply a product rule. So, and then it also works that way for quotient rule. I'll go ahead and write these out real quick. We all know these, and then if we have a quotient and we take the derivative in Cal 1, we know it's not just you do the derivative of top and bottom separately, right? You have to use the formula. Okay, well, when we're doing antiderivatives, it's the same ball game, all right? If you're trying to find the antiderivative of a product, it's not just the product of the antiderivatives. And if you're trying to do the antiderivative of a quotient, it is not just the antiderivative of the top and bottom separately. Unfortunately, that's not the case. If that were the case, I think calculus would be a much easier course, just overall, in general. So we don't have that happening. And I want to point that out because right now, do you see that we actually have a quotient? We have a numerator and denominator. We are not allowed to just look at the top by itself, find the antiderivative of each one, and then look at the bottom and find the antiderivative. No go, all right? We're not allowed. We are, at this point, the only thing we can do is take the antiderivative if there's pluses and minuses between things, but no products and no quotients yet. We clear? That's the biggest mistake I see on problems like this. So with that in mind, it would look like maybe we can't do anything here, but algebraically, we can actually simplify this. Because we have a single factor in the denominator and we have multiple factors in the numerator, we can just use properties of fractions to split this up into 4 separate fractions. So I'm going to write this as 2x over cube root of x plus the square root of x over cube root of x minus 4 over cube root of x plus x cubed over cube root of x. Okay, that's allowed. That's algebraically, that's fair, right? That's a legal move. I can go one more step and I can rewrite this as x to the 1/3, x to the 1/2 over x to the 1/3 minus 4 over x to the 1/3. What am I doing here? Hold on, I need to ask somebody. We left off last time. Let's see where we were. Let's see who's up today. Today we're gonna have Cheyenne, then Peggy, then Nicholas, then we're gonna go for Alexis, Stephanie, Youssef. Okay, so who did I say is up? 3, 4, 5. Sorry, I'm losing my mind. Okay, Cheyenne. Cheyenne here?
Yes.
Okay, Cheyenne. Oh, you know what? Let me bring up my list. Forgot to put that up here. Cheyenne, why do you think I'm doing this? Why do you think I'm actually going through this process of rewriting everything, putting things as rational exponents? Like, what do you think the purpose of this is going to be?
Would it be easier to go through the problem, like thought-wise, without making too many incorrect steps?
Okay, but I mean, why did I do this though? Why did I decide to split it up and then now I'm converting all the radical notations to rational exponents? Like, do you see where I'm going with this? What can we find the antiderivative of right now? Like, what is the only thing we really know how to do that we actually have a formula for?
I'm not too entirely sure.
Okay, what is this that we started with?
Oh, it would be the powers, right?
Right? X to a power, right? That's what we have a formula for. Other than that, we would have to know it from like, oh, you know, the antiderivative cosine is sine, okay? But otherwise, the only formula we have is the power rule. So what I'm trying to do here, Cheyenne, is I'm trying to rewrite this expression where I can look at each term as x to a power. That's what I'm trying to do, okay? So I'm going to try and now combine these x's together, those x's together, those x's together. This x, I'm going to move it up to the top. And so this is just algebra. I have to use, you know, some properties here that when you have x to a power, I'll put it up here in the corner. If you have x to a power divided by x to another power, then you will subtract the powers, right? You'll take the n and subtract the m. That's an exponent property from college algebra. So when I look at this expression here, I'm going to have 2, and then let's see, Cheyenne, what would I get? I'm going to have x to the first over x to the 1/3.
Would it be x to the half?
Okay, so you're trying to do 1 minus a third, right?
Okay, so it would.
So look, everyone is going to be at a different place here, okay? Everyone in the class. I've been doing this too long. I know there are going to be people who are going to have trouble with that, and there are going to be people who can do it in their head, no problem, okay? As a Cal 2 student, though, you want to get to the point where you can do that in your head. If not, it's just going to slow you down so much. These tests, you won't be able to finish them because you're spending too much time just trying to figure out what, you know, addition, subtraction, and fractions are. So I'm not picking on you, Cheyenne. I'm just saying I know there are people in here that still struggle with that. So that's something, that's a skill you're gonna need to work on and get fast with, all right? Okay, so 1 minus 1/3, that's 2/3. Okay, and then plus, okay, on the next one, I have to do a half minus a third. I'll show you all a quick trick on how you can add and subtract fractions real fast. All you have to do, let me put it down below this. Okay, if I have a fraction, let's say I'm adding or subtracting another fraction, then all I have to do is first multiply a and d together. So multiply those two together. And then whatever the operation is, whether it be plus or the minus, you're going to put that here. Then you multiply these together, the b times the c, put that here, and then divide all of that by the two denominators multiplied together, b times d. And that is going to be the answer, all right? So like, for example, on this one right here, what I would do real quick in my head is I would do 1 times 3, that's 3. I would subtract 2 times 1, which is 2. And I put that over 2 times 3, which is 6. And that's going to give me 1/6. All right? Make sense? You can also do it other ways, but that's kind of the way I do it when I can't. When they don't have the same denominator, that's what I do. Okay, so we're going to have 1/6 here. Okay, on the next one, all I'm going to do here is bring the x to the 1/3 up to the top, which makes it negative. Now that's important because if I'm going to find the antiderivative, the only thing I can find the antiderivative of is x to a power. And I already said that if you have a fraction, you can't do a quotient rule. So I have to bring the x up to the top so it looks like x to a power, all right? So it's a very critical step. And then my last one here, what am I doing? I have to do 3 and take away 1/3. So I do 3 over 1. Then I just do this real quick little 3 times 3 is 9. So in my head, 9 minus 1 times 1 is 1. So 8 over 3. So 8/3. Okay? Any questions? All right, now, we haven't taken the antiderivative, right? This is just f of x. So now it's time to find the antiderivative. And because I have 1, 2, 3, 4 terms, they're separated by addition and subtraction, I can do each one of them separately. And then let me also point out that just like we had in Cal 1, when you have a constant in front of a function and you take the derivative, the constant comes for the ride, right? So like if I take the derivative of, let's say, 4 sine of x, the 4, because it's attached to the front, just comes for the ride, and the answer is 4 cosine x, right? So when you do antiderivatives, it works the same way. That's good news. Okay, if we have a constant, it's just going to come for the ride. So I'm going to start taking antiderivatives here. First of all, so I'm getting the antiderivative. So first of all, the 2 is going to come for a ride. And then what I'm going to do is I'm going to recognize that the n is 2/3, right? So in my formula, if I'm going to do this really slow, I know my formula is 1 over n plus 1 x to the n plus 1. Okay, does everyone see that's the formula? I'm good with that? Then I'm going to do the next one. Plus, okay, here I'm going to have 1 over, this time n is 1/6. So I'm going to have 1/6 plus 1 x to the 1/6 plus 1. And then the minus 4 is going to come for the ride. I'm going to have 1 over negative 1/3 plus 1 x to the negative 1/3 plus 1. I don't know why I'm writing so sloppy today. Sorry about that. And then finally, I have, let's see, 1 over 8/3 plus 1 x to the 8/3 plus 1. And then remember, we always have that plus c at the end. Okay, lots of fractions we have to add together now, right? So let me continue. I have 2 times 1 over 2/3 plus 1. So let me just again tell you real quickly what I'm doing in my head. I'm doing 2/3 plus 1, right? 1 is 1 over 1. And then I'm just doing real quick cross, and then, you know, go across and then go across the bottom. So 2 plus 5, 2 plus 3, which is 5 over 3. Make sense? 5/3. And then x to the, well, the good news is you already did this, right? We just did that same thing. So that's going to be 5/3. And then plus, okay, 1 over 1/6 plus 1, 7/6. X to the 7/6. Minus 4 times 1 over negative 1/3 plus 1 gives you 2/3. X to the 2/3. Plus 1 over, let's see, do the little thing here, 3, you should get 11/3. X to the 11/3 plus c. And then there's still a little bit of cleaning up to do, right? I've got to take these, 1 over a fraction just flips the fraction. So all of those are just going to flip. So I get 2 times 3/5 x to the 5/3 plus 6 over 7 x to the 7 over 6 minus 4 times 3/2 x to the 2/3 plus 3 over 11 x to the 11/3 plus c. I could do one more thing. I could clean up these things. I could make that 6/5, and over here I could make that 12 halves, but that turns into a 6. So I could just change that right there to 6/5. Change that right there to a 6, minus 6. And then I'd be pretty much done. Okay, any questions? We're good?
On the exams, would we be able to have our calculator?
Yeah, you can always have a calculator on your exam. All right. So now let's move on. Another example. So let's say f of x is equal to sine x plus secant x tangent x. So this one, let's see, let me ask. Peggy? How's it going, Peggy?
Oh, it's going good.
Good. So we have two terms here, right? Separated by addition, subtraction, or addition. So you can just look at them separately. So really, I'm just asking you, Peggy, do you know what the antiderivative of sine is?
Cosine
Okay,
or negative cosine.
good. Okay,
Is it-
negative cosine, good. Negative cosine of x. All right. And then same thing, do you know what the antiderivative of secant x times tangent x is? So do you remember from Cal 1 what you take the derivative of that gets you that?
Not really.
Okay, all right. So this would be, you would have to go off your formula sheet. So look, from Cal 1, everyone should know the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. The other three, you don't necessarily have to have memorized, but this one, I mean, they do come up quite a bit. So if the sooner you like memorize those, the better. Let me see, I think it's on here. Yeah, right here. So if the function is secant x tangent x, the antiderivative of that is just secant. So this is just secant x plus c, we're done. So that problem, that was just an example of where you need to know stuff in order to do it. All right, last example, and this one is the most interesting. 2 plus x squared over 1 plus x squared. All right. Let me first start off by reminding you, you cannot do the top and bottom separately, right? I just said that a moment ago. It's a quotient. You're not allowed to take the antiderivative of the top, then the antiderivative of the bottom, just put them together. No go. So, what do you do? Can we do what we did in the previous problem, the one right here? Can we do what we did here, where we did like each one on top over the bottom and then rewrite these powers? We can't. Why not?
Because there's two terms in the denominator.
Terms in the denominator. So it really, I mean, it wouldn't work well that way. Well, I mean, we could do it, but then you wouldn't be able to simplify the x's. That wouldn't work. So, I mean, technically speaking, we could do this. We could write the 2 over the 1 plus x squared, but then we would also have to put plus the x squared over the 1 plus x squared. And what I'm saying is you can't like clean up these x's. You can't cancel those out or do anything because you've got 2 terms in the bottom. Okay, so I'm going to open it up to everyone. Does anybody have any idea on how to do this? I mean, I don't expect you to, but you never know. Sometimes people just try something.
Could you try and move the denominator up to the numerator, maybe?
Okay, so something like this. Maybe we could rewrite it this way. 2 plus x squared. And then if we brought the whole thing on the bottom up, it would have to look like this. Like that. That's what it would look like. Unfortunately, now we have a product. And so you still can't do the antiderivative of each one because, well, calculus just isn't that friendly. So you can't.
What if we multiply by 1?
Pardon? Multiply by 1?
Yeah, but using the denominator over the denominator again.
So just almost like we did like in calculus when we would do like rationalizing or something like that, we would just multiply top and bottom, maybe it would make it better. Is that
Yeah.
what you're kind of saying? Okay. Maybe. I think that might just complicate things. I don't see that if we do that, it's going to get any better. I think it'll just look worse. Nothing's going to cancel.
Could you maybe factor it? Like factor the numerator and the denominator?
If it was factorable, it's not factorable in this case because it's a sum of two things. So the most we could maybe hope for is maybe it was a difference of squares and then we could try and factor, but it's something squared plus something. So let me try and lead you to this, all right? Because maybe it's not so obvious. Is there anything in this expression that is like making a small little flicker of a light bulb go off in your head? Is there anything at all?
Well, the denominator, the antiderivative of the denominator is the tangent inverse.
Okay, so does everyone see that? Does everyone see that 1 plus x squared on the bottom? And that was one of those ones that I put the stars next to. I was like, remember this one, remember this one. We know this. If we had a little function, little f of x, if it was 1 over 1 plus x squared, if that's what it was, then we know the antiderivative of that is arctangent of x plus c. Okay, that we should know because I told you to memorize that. We don't quite have that though, do we? Because we got all that crap up top. So maybe you try and get real tricky and you're like, okay, here's what I'm going to do. Instead of writing it like that, here's how I'm going to write it. I'm going to go 2 plus x squared times 1 over 1 plus x squared. That's the same thing, isn't it? And then you're like, ha, 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 I can do this. The antiderivative of that is arctangent x. And then the antiderivative of that is 2x plus 1/3 x cubed, because all you did there was took the antiderivative of each one separately. Well, you just violated a major rule. You had a product, and then you found the antiderivative of each one separately. Can't do that, not allowed, okay? But the 1 plus x squared in the bottom is the key to the problem. It's just, it's not like this. You can't go that way. So, you ready? I'm going to show you how to do this. And this is probably the first problem that I'm showing you where it's not obvious. And once I show it to you, you're going to be like, oh, okay, well, I didn't think of that. But now that I see that, now I know I could do that if I needed to again in the future. And that's what a lot of the rest of this class is going to be like. It's like I keep showing you these things. You're like, holy shit, I never thought of that. Okay, well, I guess I can do that from now on. And that's just, I just keep on showing you a bunch of things like that. And then you start to develop this intuition on things, all right? So the way I'm going to approach this problem, I'm going to do 2 different ways. The first way is going to be very kind of like methodical and logical, and it makes sense. The second way is going to be like, oh, you tricky, you know what? You know, you're going to be like, come on, man, that's not fair, right? Okay, so here's the first way. What I'm going to do is start with long division. Yes, I said it. Long division. So what I'm going to do is I'm going to take the numerator, which is x squared plus 2, and I put it in descending order. And then I take the denominator, which is 1 plus x squared. I put that in descending order. And then I play the good old long division game. And the long division game goes, okay, take this and see what you need to multiply to get that. So what would we need to multiply x squared by to get x squared? 1, right? And then what we do is we multiply each of those by 1 and stick them underneath. So we get x squared, and then we get plus 1. And then we come through and subtract this row. Now, if you're sitting here going, I don't remember long division. Well, you took college algebra and you passed. So you need to go remember it, okay? Long division is going to just keep coming up in this class, all right? But go get freshened up on it, all right? So you go, these cancel, and then you get a 1 here. And so now you say to yourself, okay, what does it take to turn x squared into 1? And you can't turn x squared into 1. So you're done, and that's your remainder. So what you put up here is plus your remainder over the divisor. So what we're saying is that this original function, little f of x, is really 1 plus 1 over, I'm going to change the order of that, 1 plus x squared. And now you can find the antiderivative of each of those separately because you have addition between them, don't you? So
I had a question about long
Yep.
division.
yes.
Sorry to cut you off, by the way.
No, I told you to do that, please. No, seriously, because I mean, it's hard to raise your hand here, you know.
Yeah, fair. So I remember in Cal 1, my teacher taught me that there's a long division way to do what exactly you're doing. But she also taught us that there's a shorthand way of doing it called synthetic division. And I was just curious if, like, I don't know if we're going to have another problem like that and if you remember it or prefer it for this class, but if maybe you can do an example with it just because I'm a little bit foggy about remembering that, or I can just look it up at my own time if you want to.
No, the thing is you can't use synthetic division here. So maybe one of your classmates can help out here. Why can't we use synthetic division? Does anyone know?
Because of the x squared, right?
That's right. You can only use synthetic division when your divisor, the thing that's outside here, is a linear expression.
Okay.
So had it been linear, then I may have done synthetic. But so synthetic division is definitely preferred because it's fast, but it's limited because you can only use it when your divisor is linear. Long division works all the time, but it's long, right? So it's a little bit less preferred. So I would, if you're kind of, you know, unsure about either long or synthetic division, just, you know, just go to YouTube or something and go get freshened up on it. But I would say, look at the long division. I can't even remember a time. I'm trying to think of down the road where we're going to use synthetic. I don't think we are. I think it's always going to be long division. Okay, so I'm going to take the antiderivative of each of these now. Well, I'm not going to. Someone else is. I think I'm lost. Story of my life. Did Alexis make it here today?
Yes, sir.
Okay, how's it going, Alexis?
Hey, I'm doing good.
Okay, I'm gonna call on you then. Yeah, what's the antiderivative of that?
Of 1, just 0, right?
Antiderivative.
Oh,
What do you take the derivative of to get 1?
1 x.
X, okay.
Yeah.
And then plus, now what's the antiderivative of 1 over 1 plus x squared?
Tangent.
Well, that have to be x over, I mean, I'm a little confused on that.
You shouldn't be. You shouldn't be, because we just talked about it. Okay, so I'm not sure if you were here last class, but I just
I wasn't here last class.
you were not, right?
No, I was not, yeah.
All right, did you watch the video?
I watched the video, yes, sir.
You did? Okay. I thought I had just put this up. I erased it. It was brought up by somebody, I don't recall who. Was it Ross? Who recognized? I think Ross saw the 1 plus x squared in the denominator, right? And we were thinking, okay, if it was 1 over 1 plus x squared, then the antiderivative would be arctan. So we just talked about that, right? And that's
Yes,
exactly what we have here now.
Oh,
So-
yeah, exactly, yes.
Got it? Okay.
Yeah, I see what you mean, yeah.
Okay. There we go. So that's it. We're done.
All right, cool.
All right. So now that's one way, right? I said I would show you a short way. I mean, just kind of, yeah, that kind of makes sense if we use long division, but I'm going to show you kind of a really clever way. Check this out. And if this bothers you, like, I'll understand this bothers you, but at the same time, like, get used to it, because there's going to be a lot of things I do that you're going to be not happy about. Okay, so just watch this really clever move. Okay, I just rewrote the 2 as a 1 plus 1. And then what I'm going to do is I'm going to split the fraction, and I'm going to take the 1 and put it over 1 plus x squared, and then I'm going to say plus, and then I'm going to take the other part, 1 plus x squared, and put it over 1 plus x squared. And what I get at the end of this is 1 plus x squared plus 1, which is exactly what we had just a second ago, right? And then I can find the antiderivative. And I didn't need long division for that. So that's just clever, right? That's just clever. Not every problem would work out that way. This one, it does. So I think the way that you would actually like get yourself to something like this is to be looking at the original problem and going, man, I really wish that was 1 plus x squared on top. And then you're like, wait a minute, the 2 is a 1 plus 1, so I could kind of make it a 1 plus x squared. I would just have a little 1 off to the side. So now you kind of seen that. We move on. All right, now, back in Cal 1, I hope that you learned that if you have, so this is from Cal 1, if we had a function where we had time here and distance here or position, okay, that if we were given a function, let's call it, let's see, what am I using in my notes? I forget, oops, wrong one. S of t. So we're going to call this function s of t. So the x variable is actually t. We're using t instead of x. And then the position is s of t. So if we're given a position function, s of t, in Cal 1, then when we take the derivative of that, we get a new function. And that new function is going to be time. But what is the actual derivative of the position function give us? Y'all remember from Cal 1? It's a new function. It's the derivative. But what does it represent, like physically? It's not the position anymore. It's the what?
Is it a velocity?
It's the velocity, v of t. So this first function, if it's position, then if you take the derivative of that, you get the velocity function. So this gives you velocity. And then if you take the derivative again, so the derivative of the derivative, so if you do the second derivative of the position, which really means the derivative of the velocity, what does that give you?
Acceleration.
Acceleration. Okay, so what you have here is time, and then what you have here is acceleration. And yeah. All right. So that was something hopefully you all learned in Cal 1. Start with position function, take the derivative, you get velocity, take the derivative again, you get acceleration. All right. What I've always found kind of gets lost in things is, like, let's say we're measuring it in hours. And the distance, let's say we're measuring it in miles. Okay. Then when you look at the derivative of this function, it's the slope, right? And slope is rise over run. And since rise is miles and run is your time, then your velocity should be the ratio of those two units. And I hope it makes sense to you that then the velocity would be measured in miles per hour, right? That's how we measure the speed of something. But it's just these two things divided. And then when you look at the acceleration, it's the same thing. We're going to take the derivative of this guy, And so the acceleration should be measured in whatever this is divided by time. So what you get is that the unit for acceleration should be miles per hour per hour. And that's why in physics, when you talk about acceleration of gravity, you say like negative 9.8 meters per second, right? That per second is because you've taken the velocity and divided it by time again. So you've taken miles per hour and divided by hours again. So you get a double unit of time. I hope that makes sense. Okay, so that's Cal 1. Cal 2, now that we know antiderivatives, we should be able to start with an acceleration function, go back up to the velocity function by taking the antiderivative, and then once we get the velocity function, we should be able to go back up and recover the position function, right? Because we have the antiderivative now. But that seems like that can't be true. I mean, I guess we can take antiderivatives, but I want you to think about this, because this is kind of a deeper question. If I tell you exactly where something is at every point in time, so if I give you the position of an object in space at every point in time, that's a lot of information, isn't it? So you should be able to, from that, get the speed at every point in time. And we can by taking the derivative. And you should be able to figure out the acceleration at every point in time. So knowing the position at every point in time is a lot of information. But if I just start out by giving you the acceleration of something at every point in time, doesn't it seem kind of weird that you could ever get back and tell me where it was at every point in time? Right? If all I tell you is, don't even think about acceleration, just think about speed. What if I told you how fast a car was traveling at every point in time? Are you going to be able to tell me where it is? No, right? You shouldn't be able to, but it turns out we actually can. We just need a little bit more information. You need to tell me how fast it's going at every point in time, but then you just got to give me one more piece of information, just one little thing, and then I can figure it out. Let me try and illustrate this with a picture. Okay, and I think we'll start off with this example. Let's say that this is a velocity function, velocity and time. It tells you where something is at every point in time. If I take the antiderivative of that, what will it give me? A new function, right? So if I do the antiderivative, it gives me a new function. But does it give me just one function? No, it gives me a family of functions, right? So remember, this is what we talked about last class. There's an infinite number of answers. But one of those is the answer that I'm looking for. So all you would have to give me in order for me to be able to nail down which of those family members it is just give me 1 point. Give me 1 point on one of them. If you just give me 1 point on one of them, I will be able to tell you exactly which function we're talking about. So the analogy is like this. If you know how fast something is going at every point in time, I will be able to tell you where it is at every point in time if you just tell me where it was at one point in time. Say it again. If we know how fast something is going at every point in time, I will be able to tell you where it was at every point in time if you just tell me where it was at one point in time. Okay, so there's not a whole lot of information more that we need. All right, let's do this. Bring my notes up here. Hey, what happened? Okay, so this is me just reminding you that if you have position, that the first derivative is going to be velocity and the second derivative is acceleration. And then let's get to example. Example 2 here. If the acceleration of an object moving in a straight line is a of t, so they give us an acceleration, a of t is equal to 24t minus 6. And they tell us that S of 1 is 7, and V of 2 is 41, then we want to find the position. I'm not going to write it down. You can see it there. So the first one is to find the position function for the object. All right, first things first. We start with the acceleration. Let's get back to velocity. So if I want to know what the velocity function is, what I need to do is take the antiderivative of that. So here we go. Who's up, who's up, who's up? I've lost my place again. How about Peggy? We got, right? Peggy, we got. Nicholas. How about Nicholas?
Hello.
Nick, can I change it to Nick? And change it to Nick. All right, Nick. So what is the antiderivative of 24t minus 6? And just keep in mind, we're using t instead of x now.
12t squared minus 6x.
6t, yes. 12t squared minus 6t.
Or t, my bad.
That's all right. You said t on the first one. Okay, now that is almost there. It's an antiderivative.
Oh, plus c.
Plus c, okay. So what we know now is that the velocity function is the antiderivative of the acceleration, and we've got this family. Now, Nick, there's something given in the problem, some information that's going to be very useful to us. Do you see it?
Yes.
Okay, which part?
It's v of t is like 7, and then you also have 41, and that's when t's at 1 and 2.
Okay, so this piece right now is the part that's important to us. We're being told that the velocity at 2 is 41. That means when I take this function that I'm not quite sure what it is because it's a plus c, when I take 2 and plug it in there, I should get 41. So let's go ahead and plug 2 in for t. If we plug in 2 for t, we should get, let's see, 2 squared, that's 4. 4 times 12, that's 48. Minus 6 times 2, which is 12, plus some constant should equal 41. Does everyone follow that?
Yes.
Okay, now let's just solve this. This is 36 plus c equals 41. And that means that c is 5. Just subtract 36 on both sides. So Nick, do you see now that where originally we had the plus c and didn't know which of the family members it was, do you see that with that one piece of information that we now know what c is, and therefore we know the exact velocity function? Is that clear, Nick?
Yeah.
Okay. Everyone got that? Now that we know the exact velocity function, let's go back and take the antiderivative again, and that'll get us position, and it'll be within a family. And luckily for us, they tell us something about the position at 1, that it's 7. So the antiderivative of this will be our position function. And we're moving on past Nick. I believe our next volunteer is Stephanie. Stephanie, Stephanie? Stephanie here?
Yeah.
Okay, Stephanie, so what you got? Antiderivative of this.
Would it be? Hold on.
Take your time.
Six t to the 4th.
What'd you get?
6t to the 4th.
Are you trying to do this one right here?
Yeah.
Okay, so antiderivative 12 comes for the ride. Then you do 1 over n plus 1. What's n plus 1?
3.
3. And then you do t to the n plus 1, so t cubed, right?
Yeah.
And then you do 12 divided by 3, which is 4, right?
Okay.
4t cubed should be the antiderivative of that. Is that right, Stephanie?
Yeah.
Okay, and then minus, now the next one, we do the same way, and because time, we're just gonna have to crank this out. Plus, now I'm gonna say plus C again, but I'm not gonna use C because we already used C and I just don't want there to be confusion. So I'm gonna use another letter. I'm just gonna use capital D. I'm gonna make sure it's a D and not a 0. Okay, but Stephanie, how are we gonna figure out which family member it is? What can we use?
The
What? What information do we have that's going to help us nail down the value of that D?
the SI equals 7.
S of 1 equals 7. So the fact that S of 1 equals 7 means that when we plug 1 into this, we should get a 7 to come out. So plugging 1 in is actually kind of easy because 1 to any power is 1. So it should be 4 minus 3 plus 5 plus D equals 7. And that's just 6. I think D is 1. Okay.
Yeah.
So now we actually have the position function. S of t is exactly 4t cubed minus 3t squared plus 5t plus 1. There it is. That is the position of our object at every point in time.
I had a quick question about this problem.
Yes.
For exams and quizzes, when we're trying to do similar problems like this, if we don't make a new constant, in this case scenario, you did D and you did C for the velocity function. If we kept it like as C, would you take points off?
No, no. Mm-mm. No.
Okay.
Yeah. So let me, I'm gonna set up a problem, but I'm not gonna do it, okay? This will come up in your homework. Let's say that let's do the same exact problem, but I'm gonna change something. I'm going to change this V of 2. That was very useful information, wasn't it? I'm gonna change that to S of 0 equals -4. Okay, so let's try and I'm going to run through this quickly. Do you notice that I still gave you 2 pieces of information, but they both have to do with the position, right? You no longer have any information about the velocity. So the question becomes, is this enough? So let's go through the process. First thing we would do is find the antiderivative of the acceleration, which would give us velocity. We wouldn't know what c is, would we? And we wouldn't be able to figure out what c is because we don't have any information about velocity. So we would be stuck right here. That's where we would be. You all okay with that? That's what we would have. Well, we wouldn't freak out. What we would do is we take the antiderivative of that. Okay, so let's just do the antiderivative of this. That would give us our position. And if we do the antiderivative here, we should get 4t cubed minus 3t squared. Now, this is the cool one. Plus, what's the antiderivative of c? So what would be the antiderivative of 5?
5x.
Or 5t, right? Because our variable's t.
Oh, right.
So the antiderivative of a constant should be the constant times the variable. So I'm going to put here c times t. But I always have to add a constant when I do an antiderivative. So I need to do plus here and see, here's where I wouldn't want to use c again. I would want to use d. Does that make sense to everyone? antiderivative, 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 and then we have to do the plus constant because you do that every time you take an antiderivative. That make sense? Okay. Now, this looks like it's terrible because there's two things we don't know, right? We don't know C and we don't know D. However, we know that S of 1 is 7, and we also know that S of 0 is -4. So when I plug 1 into this thing, it should spit out 7. Let's do that. Let's plug 1 in. 4 minus 3 plus what? Plugging in 1. 4 minus 3 plus C plus D equals 7. Do y'all see that? Replaced all the T's with 1s, and I still have a C and a D there. Okay, let's go to the other, well, I'm gonna stop here because does everyone agree right now that we have this, C plus D equals 6. So you can just combine the 4 and 3 together, get a 1, subtract 1 on both sides. You get C plus D is 6. You can't solve for C or D. You have an equation with 2 unknowns. Over here though, when we plug in 0 for T, so I'm doing this one now, when I plug in 0 for T, then I would get what? D? Just the D, because all these T's would become zeros. So all I'd be left with is that D equals -4. But you see, once I know what D is, I can plug D in here, now I can get C. So I'd have everything. Okay. I can already tell you that there's a problem that you're going to run into where you're going to have C plus D over here equals 6, and then over here you're going to have something like 2C minus D equals 5. And so what do you have there? 2 equations, 2 unknowns, right? So you got to go back to college algebra and solve a system of linear equations, either using elimination or using substitution. Okay, so just be ready for that because it's going to come. System of linear equations. All right, we're not ready to move on yet. I want to show you something really cool. So, well, cool is relative, isn't it? Let's see, acceleration of gravity on Earth. So 9.8 meters per second is the acceleration of gravity on Earth. Hopefully we all know that. Okay, in feet per second squared. So let's see. Yeah, that's good. So there we go. It's about 32.1745, something like that. Okay, so I'm going to convert it from meters per second to this. So here's what we got. On Earth, the acceleration of gravity is negative, and we're going to say approximately, negative 32 feet per second. So that is actually an acceleration function. I'm going to call it A of t. It's a constant, isn't it? If you drop something on Earth, the acceleration is a constant. And it doesn't matter what you drop. Now, we do have to neglect air here because air does play a role. But if we take air out of the equation, negative 32 feet per second is good enough. Now, does anybody remember this from college algebra or some other class that you took? It's a formula that says this: the position of a falling object. Let's see if this looks familiar at all to you. S of t equals negative 16 t squared plus v naught t plus s naught. Okay, just nod your head or thumbs up or something like that if you remember seeing that anywhere before in like physics or some other class. You know, a couple of you. What this formula gives you, it says, look, if you take, let's say, a building and you were to drop a rock off that building, then if you know S of t, which is the height of the building, and you know v of t, which is the starting velocity. And so if you just drop a rock, the starting velocity is 0 because you just drop it. But you could actually throw a rock down or throw a rock up, and that would be the starting velocity. And then that's it. That's all you have to know. The height that you drop it from and the starting velocity. And from that, this thing will spit out exactly how high it is off the ground after a certain amount of time. Okay? And if you take this quadratic and you set it equal to 0, then you can find how long it would take to hit the ground. That's what you would be solving for. So this formula right here is a position function. Guess where it came from? Well, let's do it. We're on Earth, right? We're dropping a rock from a building. Okay, so we're on Earth. So once you drop something, what's the only thing acting on it? The only force? Acceleration of gravity, right? So this is the acceleration function for that rock. So let's see if we can't get back to the position function. So if I ask you to take the antiderivative of this, what's the antiderivative of a constant? Forget the feet per second. What's the antiderivative of negative 32? Negative 32t, right? That's the antiderivative. Plus some constant that we don't know. And then we do the antiderivative again to get position. What's the antiderivative of negative 32t?
Negative 16t squared.
Negative 16t squared. Plus the antiderivative of c, which would be c times t, right? Plus we would have a new constant, wouldn't we? That's what we'd have, right? Now, do y'all see that this formula and this formula are exactly the same things? Do you see that the S sub 0 is that d? That's our starting height. That's how high the object would be at t equals 0. I think you can see if you just think about it. If you plug in 0 here and 0 here, the only thing left is d. So that should be how high you are at 0 time. This is your starting height. Also, this this v naught, this c right here, yeah, that is your starting velocity. How do you know that? Again, plug 0 into velocity, the c is still there, so that should be your velocity at the beginning. What I'm telling you is that if you go to any planet, okay, go to any planet, if you can measure the acceleration of gravity on that planet, you can generate its position function for any object falling on that planet. You just have to be able to do the antiderivative twice. So the only thing that makes Earth's position function unique, the only part of it that is unique to Earth is the negative 16. Because that comes from the acceleration of gravity here. We go to Mars and everything else in the formula would be the same except for that negative 16 out front. It would be something different. Does that make sense? So it's pretty cool. You can generate the position function for any object with mass if you can just take the antiderivative. All right, now I'm ready to move on. Any questions or comments while I'm getting my next thing up here? Whoa. How in the world did that happen? I accidentally grabbed all of y'all and put y'all on my screen. All right, here we go. So we need to get some notation and language out of the way. It's kind of a pain in the butt. You know, you've probably noticed this, that if I write down some function and ask you to find the antiderivative, I've been having to like tell you, find the antiderivative, find the antiderivative, find the antiderivative. It would be nice if we had a notation that would kind of like make that faster. Kind of like when we were in Cal 1, if we had a function and we wanted to take the derivative, we could just put this little prime mark on it, right? And that little prime meant take the derivative. So it's like a quick notation for it. Or we could say like take the derivative with respect to x of the function or something like that. We had a quick way of saying, hey, go take derivative. Well, same thing goes with antiderivatives. We have a notation that we use to kind of let everyone know what we're trying to do. And here's the notation. Let's say we have a function little f of x and we want the antiderivative. What we do is we put this stretched out, it's like an s that's been stretched out, all right? And then next to the function itself, we put this little thing dx, and that's actually multiplication right there. And that tells everyone it's time for you to take derivative. And the thing we're taking derivative of is this, all right? And of course, the answer to this will be some capital F of x plus some constant. And so there's names for this thing, all right? This whole thing over here is called the indefinite integral. That's what it's called, the indefinite integral. So you're gonna start hearing me say antiderivative less and less. You're gonna hear me saying, find the integral, or find the antiderivative, or find the indefinite integral of this function. They're synonymous with antiderivative. The symbol, this actual symbol here, is called the integral sign. And it actually comes, I told you it's like an S that's been stretched out. We're gonna find out later, after chapter 6, that it actually comes from the old Greek sigma notation. It's just this very special kind of thing we do with sigma, and it becomes this weird S-looking thing, okay? But we'll find that out later. The function we're integrating, okay, the actual function we're integrating is called the integrand. Was there a question? No? Okay.
I actually had a kind of like minute question to ask.
Mm-hmm.
Does the dx signify the respect of what you're taking the integral of? So can you get like d theta for doing trigonometric functions and stuff?
Yeah, so look, this dx is the most difficult thing to explain to you right now. It's hard because we don't have the precise formulation of this yet, but here's the way I want you to look at this right now. This dx, which is called the differential, okay? It's called the differential. I want you to think about it as right now, it's just keeping track of what your variable is, all right? Here's a way you can look at it. Another way you can look at it. Let me clear all this crap out of here. Clear, okay, go back. So here's a way I want you to think about it. If I ask you to take, go back to Cal 1, if I ask you to take derivative of x squared, right? Well, you know what, let's do it this way. Okay, y equals x squared. Let's take the derivative of y with respect to x. That should be 2x. Do we all agree? Now, I'd like to multiply both sides of the equation by dx. You with me? Now, that little dx is the differential we're talking about. So right now, if I were to say, find the antiderivative, what would be the antiderivative of this dy? Look at that as being like 1 dy. So what's the antiderivative of 1 with respect to y? Careful. What's the antiderivative of 1 with respect to y? Y, right? Yes? And then what's the antiderivative of 2x with respect to x?
X squared.
X squared. So you see the integral takes us back up there? But that dx is actually sitting next to every function we've ever taken a derivative of. So right now, we're not going to get too much into it, other than to just know it needs to be there, and that it keeps track of the variable, all right? Now, keep going here. This capital F of x is called the antiderivative, right? And then this c, we actually have a name for it now. It's called the constant of integration. The constant of integration. Whoa. I must really want that to be the constant of integration. Why is that not getting smaller? There we go. All right, so this is all just notation now. We have the indefinite integral, we've got the integral sign, we've got the integrand, we've got the differential, we've got the antiderivative, we've got the constant of integration. Great, great. All right, we keep going. The process of finding antiderivatives is called integration. So just like the process of taking derivatives is called differentiation, the process of finding antiderivatives is called integration. So a lot of times when you talk about Cal 1, Cal 2, Cal 3, Cal 1 is called differential calculus, which means you're doing derivatives. Cal 2 is called integral calculus because you're doing integration. And then Cal 3 is usually called vector calculus because you're basically doing both differentiation and integration, but now in 3-dimensional and 4-dimensional space with vectors and vector fields. So differential calculus, integral calculus, vector calculus is usually the way it's broken up. All right, we're ready. We're about to dive in. We're about to it's going to start to get like serious and real now, okay? We have the power rule. We've already established this rule. Everyone should know this rule. We move on. We need it for the rest of our lives here. We've established that the antiderivative of x to the n can be one of two things, depending on if n is not -1 or if it is. And then you should become comfortable with using page 6 of the formulas 1 through 20 on your formula sheet. Let's take a look. Page 6. You should be comfortable with all of those. Like you should know they're here, okay? This is a good summary. Now, number 1 on that formula sheet, just ignore it because we haven't talked about number 1. Number 2 is actually the power rule. And I'll point out that notice in every one of these formulas, they're using u instead of x, right? They're using u instead of the variable x. So does everyone see number 2 is the power rule? You all see that? Do you see that 3 is the special case of the power rule when n is -1 because u is on the bottom? So that's almost like a 1 over x. Number 4, the antiderivative e to the x or e to the u is e to the u plus c. So on and so forth. So look at formula 17. Formula 17 is an interesting one because 17 looks a lot like something I told you that you need to be comfortable with, but I told you it was 1 plus x squared, right? Gave you arctangent. But what if it's something like, well, like it is here? What if it's something other than 1? Well, we have a formula for it. So what I'm getting at is if we had like antiderivative of 1 over 4 plus x squared dx, if we were going to do this, we actually have this formula can do it. What would a be in this formula? Because u is the x. So what would a be for us in this formula?
2 squared.
So a for us 4, right? 4 is a squared. So for us, A would be 2. So what would the answer to this be according to this formula? 1 over, is it 2 or 4?
2.
2 arctangent of, now we do this part, x over 2 plus c. Do y'all see how that formula was used? Are there any questions on that? So I would just take some time to just kind of look through this to see formulas 1 through 20, like what you have here, what you can work with. Because you don't want to be doing a problem later on where you have to find the antiderivative of secant, and you're sitting there going, I don't know how to do that. And then you realize, oh wait, that was on the formula sheet. Because anything that's on here, you're free to use on the test. So you need to be familiar with it, because you waste time trying to do something, find an antiderivative when it was here the whole time. All right. All right, we are ready to get into the first technique of integration. So when it comes to finding antiderivatives, we've already established that so far it's what we know from Cal 1, and then this power rule. That's pretty much it. But are there any other like formulas or anything else? Well, there's not really. There's 5 techniques that we teach to help you try and find antiderivatives. The 5 techniques are, first one is called U substitution. I'm just going to call it U sub. That's what I'm about to start talking about. The second method is called integration. I'm going to abbreviate by parts. We'll start that next time. The third one is called trig integrals. Fourth one is called trig sub. The fifth one is partial fractions. If I personally could rank these as being the hardest and easiest, okay, out of the 5. Let's say 5 is hard and 1 is easy. If I had to rank these, I would rank U sub as 1. I would rank integration by parts as 2, then 3, and then 4, and then 5. That's the way I would rank it. I don't know. So what I'm kind of saying to you is that it's going to get harder as we go, all right? The last 2 methods, you could argue which one's worse, all right? But I will also say that you have no hope. There's no prayer for you in doing this one if you can't do the first one, okay? So if you can't do U sub, then you're not getting to 2, 3, 4, and 5. If you can't do 1 and 2, then you're not doing 3. And if you can't do 1, 2, and 3, you're not doing 4. Does it make sense? Like you can't have holes, you can't have gaps. Everything builds, all right? So there will be problems that we do. When we get to partial fractions, there will be problems that we do that will take us like 20 minutes. And when we're done, we will be at a point where the problem now looks like one of these. And we're like, oh, okay, we know how to do that now. And then it takes you another 20, 30 minutes to take that one and get it to be maybe like that. So like some of these problems can take a long, long time. Does that make sense? All right, U sub is the first one, U substitution. So the thing that we're trying to do is this, and I think it's most constructive if we start and we try and work backwards. So let's take a function that's relatively easy from Cal 1. Just think about this. Yeah, let's do this. Sine of x squared plus 1. All right, let's just clear your minds for a second. Act like you're in Cal 1, and let's find the derivative of this. Okay, so the derivative of sine of something is cosine. And then you have to say the derivative of what's inside, which is 2x, right? Okay. So we had some chain rule here. Now, let's kind of act like we didn't do that just now. Okay, let's just act like we didn't do that problem. And let me ask you, what's the antiderivative of cosine x squared plus 1 times 2x dx? So we're looking at this, and we're asking ourselves, what is its antiderivative? Now we know what it is, right? It's sine of x squared plus 1, right? We know that, but we're acting like we don't. So the question becomes, how do we get back to that? Like, how do we go from there back to sine of x squared plus 1? How are we going to do it? Can you split it and then find the antiderivative of each one? No, never, ever. So if I'm ever grading your test and you do that, I'm going to like throw some shit across the room, okay? Like I'm going to get really upset, all right? Because that's like the foundational thing. You can't do that, all right? All right, so how do we do it? See, there's no obvious path. Do you see that? There's no obvious path. You could say, yeah, I just kind of see it, you know, and good for you if that's the case. But we need a method, we need a technique, something to help us, right? So this first technique is called U sub or substitution. And we're basically trying to undo the chain rule. So this substitution rule is really good at trying to undo a chain rule. So what we're gonna do, these are the steps, okay? First thing we're gonna do is we're gonna look at the integrand. Okay, so everyone takes a real deep, hard look at this integrand. And what we're gonna do is try and find something. I'm not gonna say what it is because I don't know what it is. We're gonna try to find something and its derivative. So you're looking in the integrand and you're saying, do I see anything in there? And also somewhere in the integrand, its derivative is there too. All right, so I see it. I see x squared plus 1. And I see that its derivative, 2x, is there. Do you see that? So I'm thinking, oh, look, I do see something. This is my something that I'm seeing. And this is the derivative of the something. That makes sense, everyone? Does anyone have a question on that? Now, there's a couple of little catches. There's little asterisks next to this. You've got to verify something. If you see something in its derivative, the next thing you need to do is look and make sure that the derivative that you're looking at, it has to appear in the numerator and it cannot be trapped inside of anything. So right now, this is the derivative, the 2x, right? Is it in the numerator? Yeah, because I mean, we don't even really have a fraction. So it's in the numerator. Is it trapped inside something? And what I mean by that is it underneath the square root? Is it inside of a trig function? Is it inside parentheses being squared or cubed? Or does it look like it's just by itself? In this case, it's just by itself, right? That's what you need, okay? You need it to be by itself. It cannot be trapped, it has to be in the numerator. Okay, so we got kind of a thumbs up on that, right? We've got step 3, it's done. Now, the next thing is the derivative might be off by a constant. In other words, let's just say, and this isn't the way it is because this is our first example, let's say that this wouldn't have been 2x. Let's say the way the problem was given, it was 5x. So we would still see we have something, right? X squared plus 1. The derivative of x squared plus 1 in our minds would be 2x, right? What would we have though? 5x, right? Is that okay? Well, according to what step 4 says, the derivative might be off by a constant. You can be off by a constant and the method will still work, okay? So even if that's a 5x, we can still do this, all right? But you can't be off by, like, let's say that was 5x squared. No go. Because then we're off by more than a constant. It has to be x, but then any number you want in front of it. Okay. So we looked at the integral, we found something and its derivative. The derivative wasn't trapped. It's in the numerator. We're all good to go. Here we're not off by constant. So what do? Well, let u be the something from part 2 and go for it. All right, what the hell? Okay, so what I'm going to do is I'm going to make a substitution. I'm going to, over here on the side, I'm going to let u be equal to the something that I chose. Okay, that's the something we chose, right? And then what I'm going to do, and I will do this every single time I do a problem using u substitution. The next thing I'm going to do, move this over just a little bit more. The next thing I'm going to do is take the derivative on both sides of this equation. So I'm doing like little scratch work on the side here. I'm going to take the derivative of u with respect to x. And when I do that, the right-hand side just becomes 2x. And then I'm going to do one more thing. I'm going to get rid of the dx on the left by multiplying dx on both sides. Y'all with me? Now, I'm going to erase some of this stuff that's up here. It's kind of in my way. A little too much there, Chet. Now what I'm going to do is I'm going to start looking at my integrand and seeing, like, I'm going to rewrite the integral. And it's going to be in terms of u. There's going to be no more x's. It's going to be all u's. So does everyone see that the x squared plus 1 right here will be able to be replaced with the u, right? And then this is the great part about this particular problem is I have 2x dx, right? And that's exactly 2x dx there. I mean, they match perfectly. So now what I'll do is I will rewrite the integral. I want to know the antiderivative of cosine, but not of x squared plus 1, cosine of u. Times, now what does the 2x dx become? Well, what is it? du, right? And now think about where we are. This is like me saying this. I'll do it up here in different color. This is like me saying, what's the antiderivative of cosine of x dx? As long as the x here matches with the x there, like we know the variable is the right, they match up, then really what I'm just asking you is for what's the antiderivative of cosine of x, right? So what is the antiderivative of cosine of u?
Sine of u.
Sine of u. Sine of u plus c, right? Plus c. Now, what happened there? From that line, students always freak out here. From this line to this line, I actually did the antiderivative, right? So there's no more integral sign. There's no more du. Like this and this don't really matter anymore. I just was really looking at that and saying, what's the antiderivative? And we said, oh, the antiderivative is sine, right? Now, we're not done because our answer has u in it, but the original problem had x in it, right? So now I'm going to resubstitute back in what u was, right? And that's it. And we knew that should have been the antiderivative, right? Because we had cheated in the very beginning. We had started with the function. I said, hey, let's take the derivative of it, and then we try to go backwards. So what we came up with is that, yeah, our answer is sine of x squared plus 1 plus some constant. What do y'all think?
Not that hard.
Who said that?
German.
Careful, German. It's the first example.
Yeah.
Okay, here we go. You ready for another one? Look at your homework assignment for this section. 1 through 36 all. There's no such thing as doing too many problems. From here on out, there's no such thing. Like, The more you do, the better you're going to be at this. All right? I'm just going to make one up. I'm just trying to decide how far into the fire we want to go right now. Sorry, I'm really contemplating how far we want to go with this. Okay, I won't go too far. I'm sorry. Square root, the natural log of x over x dx. Oh, gosh. All right, so you should not look at this and be like, yeah, that's something from Cal 1. And you shouldn't look at that and be like, oh, that's power rule. So I'm just reminding you that we have our first things that we started class with today. This is not the case, right? The only thing we have is possibly substitution, right? So who wants to volunteer? Does anyone see something in its derivative? Go ahead, Ross.
So I mean, what I did so far is I would substitute u for the natural log of x because the derivative would be 1 over x. Is that right?
Yeah, where's 1 over x?
Well, because you have the natural log of x in the square root over x, it's essentially 1 over x times the square root of natural log of x.
Okay, good. So you have to realize that, okay, which Ross did realize that that's the same thing. The square root of natural log of x over x is the same as the square root of natural log of x times 1 over x dx. And I think that helped Ross see that something in its derivative, okay? All right, so Ross, let's keep going then. You said that because of that, the something you saw was natural log of x, and its derivative you said was 1 over x. So you made a substitution, u is equal to which one?
Natural log of x.
Natural log, right? Okay, now, Ross, when you looked at the something and you looked at its derivative 1 over x, was the 1 over x trapped anywhere? Like it wasn't under a root or anything, right? Was it in the numerator? Yeah, I mean, 1 over x is kind of by itself in the numerator. You're looking at the whole expression, all right? So it qualified, all right? So we just keep going. You take the derivative with respect to x on both sides. You get 1 over x. You multiply both sides by dx.
Mm-hmm.
And now it's just a matching game, isn't it? I mean, you're just playing a game here. 1 over x dx is going to be replaced with du. The square root of natural log of x is going to be replaced with u, right? So what did you get here, Ross, at this point? Are there any questions? No? We're going to do integral. Go ahead, Ross. What do you have?
And so now I'm at the u to the 1/2 du.
Okay, I'm going to do that on the next step. You have the square root of u, and then you replace the 1 over x dx with du.
Mm-hmm.
And then you decided, hey, now that's something you can handle because that's the same as u to the 1/2. And I guess, Ross, you're going to use the power rule now, right?
Yes.
Okay, is everyone following? Okay, so the power rule on that is going to be, so since Ross is about to do the antiderivative, there's no more integral sign. This is the step where the integral sign is going to vanish. 1 over, what do you got, Ross?
So it would be 1 over 1/2 times u to the 1/2 plus 1. So would that be 2u to the 3/2?
Yeah, hold on, let me write it down first. So the n here is 1/2, so you have 1 over n plus 1 is 1 over 1/2 plus 1, u to the n plus 1 is u to the 1/2 plus 1. Now you add those together, 1/2 plus 1 is 3/2, and then you flip it. So 2/3. u to the 3/2 plus a constant. One more step.
And then you would make it, it would be 2/3 of the natural log of x to the 3/2 plus c. Awesome.
Yeah, good job.
Thank you.
All right, what time is it? 5 minutes, one more. Sorry if I took that off too quickly. No, let's take square root out. Let's make that a, yeah, we'll just leave it. I'm not gonna do a volunteer. I'm gonna pick the next person in line. Yusuf, are you here?
Yes, sir.
There you are. Okay, good.
Would you do the same thing as last time? Would you bring out the 1 plus cosine on the outside?
You could. Do you want me to do that?
Yes, sir.
Okay, so you want me to rewrite this as 1/1 plus cosine squared x, and then you want me to separate that from the
Sine.
sine? Okay, yeah, that's completely okay.
Okay, and then only thing is that a identity right there at the bottom? The 1 plus cosine.
It's close. If it was minus, it would be, but it's not. 1 minus cosine squared x would be sine squared x. 1 plus cosine squared x is not.
Let's see.
So let's go to the method. Do you see something in its derivative?
I do see. Well, sine. Sine's derivative would be cosine. So
Okay, so everybody agree with that. Does everybody see sine x there?
Yes.
Okay, the derivative of sine x is cosine x. Do you see cosine x there?
Right.
Okay, so that seems possible, but what is it? What are the conditions about that derivative, cosine x?
it can't be at the bottom, and it can't be
Can't be at the bottom, can't be trapped. And in this case, it would be, wouldn't it?
Yes.
So that's not going to work.
Okay.
So still sticking with Yosef here.
would be instead of doing sine, can we use cosine as?
Sure, why not? So if you let u be cosine, what's the derivative of cosine x?
Negative sine.
Negative sine x. Now, we don't have negative sine x. We have positive sine x, but is that okay? Remember, we can be
off by a constant.
We can be off by a constant, right? We can be off by a constant. Would that derivative, negative sine x, we're off by a constant, is it up in the numerator?
Yes.
Yes, and it's not trapped, right? That looks promising, doesn't it? So let's go with that. We're going to go with u is going to be the cosine x, and then the derivative of that with respect to x will be negative sine x, and then we multiply both sides by dx to get negative sine x dx. And I'm just about out of time, but I'm going to finish this one up. I hope y'all are okay with that. Okay, so let's be thinking about this. This cosine right here, x is going to be replaced with u, right? So isn't that going to look like 1 over 1 plus u squared? 1 over 1 plus u squared, that's what it'll look like. The question is, what is this going to be replaced with? Sine x dx. Well, come down here. Do you see sine x dx here? We almost have it. It's off by sine, isn't it?
Right,
So
yeah.
all we're going to do is take this line right here, and we're just going to multiply both sides by -1. So we're going to go negative du equals sine x dx. And now it matches exactly. Right?
Right.
So let's rewrite the integral now. It'll be integral 1 over 1 plus u, which was the cosine x squared. And then the part in green is being replaced with negative du. And negative du is the same as -1 times du, right? So I'm going to put the -1 on top and just get rid of the negative there. And further, I'm going to put the -1 outside. And I'm going to do it outside because we know that with antiderivatives, the constants can just come along for the ride. So we can just write it outside in front as multiplication. Now, I did that, Yusuf, I did that because I was hoping you would recognize this. The antiderivative of that.
Oh,
It's arc
Arc.
cos.
Arctan.
Oh,
Arctan, right? So we're ready now. It is antiderivative time, no more integral sign. I have the -1 that's going to come for the ride, but then the antiderivative of 1 over 1 plus u squared is arctangent of u plus c. And that will be negative arctangent. What was u?
Cosine x.
Plus u, cosine x plus c. There it is. Now there's good news, we gotta go, but there's good news here. The good news is that you can always check your answer by just taking the derivative. If you take the derivative of that, you better get back what was in the original integral. Okay, we will have time to practice, but I would encourage you to at least begin the problems from this section. All right? All right, everyone, have a great weekend.
what was this section called? Or what was the number?
5.5.
5.5, okay.
Yep, this is 5.5, and so in the schedule, we're right here, 5.5. It's page 306, 1 through 36. And if you're doing your homework online, just look for 5.5 substitution.
All right, thank you.
Okay?
Well, we
All
still
right. I
have
hope that y'all enjoy this section. If you've never done substitution, it's kind of like, you know, you're going to make mistakes, but then you're going to, like you said, you know, started with sine and it didn't work, and then changed it up and it works. It's like, yeah, it's like this solving a puzzle, you know, and you're going to get that little reward if you get it right, that little feeling you get, right? Like, yeah, I got it, you know, but you're probably going to suffer a little bit too, you know?
Definitely.
Okay. All right. Have a great weekend.
All right, thank you.
All right, thank you, Professor.
All right. Have a good Labor Day. Monday's a holiday. We have class on Tuesday, but
will we still have next week or?